Okay, good afternoon, everyone. I think we're going to get started again. So welcome back to everyone here and also to everyone online. Big shout out to anyone that's in Europe if they're still awake. Hopefully we'll try keep you awake to the end of the night here with a few lightning talks that we've got planned this afternoon. So Mita and I are going to do 3 lightning talks, which are kind of specific talks on parts of the product that dive a little bit deeper into the functionality. And then we're going to have a customer presentation, and then we're going to have some XML from Don and some tips and tricks at the end. So the first thing I want to talk about is multiprocessing in FME. So who here has a FME workspace that they run that takes longer than 10 minutes to run? Good. Longer than an hour? Few of you. Longer than a day? No? And the record was 4 weeks. So that shows FME is a stable product, but it also shows we're starting to run translations that take longer and longer. I know we started working with point cloud data recently, and Dale, he asked for a client to send in some point cloud data, and they said, sure, but we'll have to ship it. And they shipped it on a hard disk, and there was a terabyte of point cloud data that came on this hard disk. Now, we can still read these data sets, but as the data sets get bigger and the types of processing that we want to do on the data increases, then our runtime starts to increase. So what we want to do in FME moving forward, and this is in 2012, is leverage multiprocessing in FME. So multiprocessing is the use of 2 or more CPUs within a single computer system. So almost every server you own probably now, and indeed every laptop computer, has more than 1 CPU on it. Currently, FME in 2011 and previously, it just leveraged 1 CPU. So it's pretty much a single-threaded process is FME desktop. So when you ran the workspace, it ran the job, and it would create 1 process which took up 1 CPU. So that was fine. We could leverage all the memory. We could leverage one of the CPUs. But we were missing out on leveraging the entire CPU architecture that you had in place on the server. So the main aim here is to increase compute-bound throughput. So in layman's terms, that basically means, increase the speed of your transformations that you're running to enable you to process more data, to get the tasks that you're running done faster and in a shorter amount of time. So how are we doing this? This isn't a magic switch at the moment. What we have to do is we have to do a little bit of configuration in Workbench. And how we do that is by using options on many of the transformers. So if you see here on this Clipper transformer here, we have the parallel processing level. Here you can choose different types of parallel, basically the level of parallelism. So the whole idea is the way FME works when it reads features in is, let's say you have an Oracle database and you're writing out to, I don't know, maybe Small World or something. So the way FME works is it pulls a feature out of Oracle and it tries to write that feature all the way through the workspace, and it tries to write it out into Small World in 1 transaction. And then it reads the next feature and it tries to write it out. But what you're going to do in many workspaces is lay down transformers. And they're so-called blocking transformers, because what they do is they hold on to the features. So let's take a clipping example. Let's say we have, I don't know, a series of states that we're trying to clip data to. So maybe we have BC, Saskatchewan, etc. And so what FME does is it basically holds all the features for that area to do the clip. And it's these group by on the features that takes all the CPU and all the memory up. So what we're essentially allowing you to do, because currently this is single-threaded, remember, so what we're allowing you to do is use this group by to essentially split the process up and assign to different CPUs. So in this instance, when you run the transformation, if you're doing clipping on all the states in America, let's say, it would basically create a process for each state in America, and then the transformation would happen much quicker, and then once it's done, it would join back again. So you can also set this option on custom transformers as well. And let's look at the levels of parallelism that we offer now. So we have 5 main levels. We have no parallelism, which you can set, which is the same as 2011 was. We have minimal. What FME does there is it looks at the number of cores on the server. So say you have 16 cores on your server, it basically divides it by number of 2s, divides by 2. So it would create 8 processes with FME. For moderate, it would create 16, so it would match the number of cores to the number of processes. Aggressive, it would create 24, and extreme, 32 processes. So these are the values you can select on those transformers, and we'll talk a little bit more about how you choose those values. The next thing is licensing. So currently, what we've allowed you to do is 1. So everything here you're gaining, you're onto a winner basically, because what we're letting you do is, if you have a base, you can now run 4 processes at once, professional 8, another 16. These aren't set in stone either, so if you are wanting to kind of scale more than that, you have a bigger server, just talk to us. We're not trying to kind of stop you from doing work here. We just don't want you firing up, you have a professional license and you have a server with 200 cores on it and you basically fire up 200 processes. That's why it's in place. We don't maybe mind you doing that, but you just want to talk to us first. Okay, so here's a few examples that Dimitri have put together for us. These are on FMEpedia as well, so you can go to FMEpedia. The first one here, we have DEM generation. So reading in LiDAR data, traditionally large data sets with many points. And we have a raster DEM generator transformer. So that's the one we're doing the group by on. So without parallelism, it takes 1 minute 10. And you can see there with the moderate setting, we have it down to 33 seconds. The buffering example, you can see the drop from 2 minutes 51 down to 1 minute 30. And I'm going to dive into this example a little bit more because it's actually quite interesting. So as I say, we have to split this data up somehow on the transformer. So if you look on this transformer here, it's a custom transformer, and we're setting the parallel processing level to moderate. But we have to break this data up. So what we've got here is we've got a road network that we're pulling in for all the roads. I think it's in Austin. So we're pulling all the roads in Austin, and we're going to buffer them. But buffering, I know, is the bottleneck in this transformation. How I know that is because I ran it and I looked at the log, and there's a timestamp in the log, and you can see where FME struggles and slows down. So what I thought I'd do is I'll split that data up. And I want to split that data up, and using the parallel processing level, use a group by and basically group the data into 8 sets of data. So when the data comes into this transformer, FME splits the data up into 8 different processes, and then the operating system basically takes those processes and assigns them to a CPU. So if you have more than one CPU, then it will leverage the CPU. But the clever thing here is we didn't actually have a group by, so I didn't really have anything to group the data on. Like, it wasn't assigned to a state, it didn't have an attribute that I could group on. So what I decided to do is create my own group by, which is quite neat. So Dimitri's used the modulo counter, which essentially assigns a number between 1 and 8 to the features coming through. So every feature comes through here, and it gets assigned a number between 1 and 8, and then the group bufferer basically uses that attribute that we've assigned to split the data up into groups. Because remember, we're buffering here, we don't really care about working on a subset of the data, we just want to buffer everything. So to split it up, we're using the group by and the modulo counter. If we had like an attribute such as road type, so we could look at motorway, primary, arterial routes, secondary, alleys, then we could have split the data up like that as well using that attribute. So this clipping transform is the biggest drop, and you can see before parallelism it was 27 minutes, and after using moderate it was 7 minutes 30. So this was, with the group by was on counties here. So this was, we used geographic area to split the data up and assign it to a CPU. One thing I will say is this is really the first iteration of parallel processing. As I say, I mean, it isn't a magic button that you just press and it happens. You have to get to know your data a bit, But if you are running jobs that take upwards of an hour, 2 hours, even half an hour, then it's worth just investing some time and play around with this to see if you can reduce the run times. And obviously, we welcome your feedback on it as well. So in summary, what we're trying to do with this is to leverage multi-core and hyper-threaded CPUs as the world moves forward. And to do that, you control the levels of parallelism, but you need to split that data up using a group by. It can give a significant performance boost if you use it properly. And there's 2 great articles, one that Dimitri wrote on FMEpedia, and one that Mark Island wrote on the Evangelist blog. If you search for parallel, you'll find both of them. Has anyone got any questions on this? Yeah, Roger, do you want to? So for those at home, they asked, do you need a 64-bit operating system to take advantage of this? And the answer is no. Yeah, it works with 32-bit just fine. But remember, with 32-bit, you only, well, you can scale the number of cores, so that's fine. You only get 3 gigabytes of RAM with 32-bit, though, so you need to think about that. There we go, yeah. Anyone else have a question? So I had a good question, actually, just before I hand over to Mita, which was why have you bothered with aggressive and extreme? It seems that every translation is fastest when you match the number of processes to the number of CPUs, right? So you've got 8 processes and 8 CPUs, so you use moderate. Why would you need aggressive and extreme? So sometimes you're not running translations that are really computationally intensive, so they're not taking up a ton of memory or a ton of CPU. You're doing things that are just slow. So let's say you want to create a workspace that connects to a web server and pulls data from a web server. Well, doing this, you can split the translation up, and if you used extreme, then you could essentially do 20 web calls at once and pull the data down that way. So just think about it. It's not always when you're working with big data sets, but you can also kind of scale requests as well. So that was a good question, I thought. Okay. So thanks for listening. I'm going to hand you over to my colleague.